Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is power plant cooling towers, and the section in the textbook is 14.7. So here are the three learning outcomes. At the end of this, you'll know the basic components of a power plant's cooling tower. You'll be able to describe the mass and energy balance for the cooling tower, and you'll be able to solve the mass and energy balance equations describing the cooling tower. So first, we just explain where a cooling tower kind of fits into the whole world of mechanical engineering thermodynamics. And they're used for cooling in Rankine power cycles primarily. So if you remember back to chapter 10, we have a Rankine cycle. And here I'm just showing the basic Rankine cycle, where we have our turbine, our boiler, our pump, and then our condenser. And the thing I want you to focus on down here is the condenser. And if you remember, we normally had something that was pretty close to a saturated vapor, maybe a slightly superheated, coming into the condenser, and then it was coming out as a saturated liquid. And that was occurring here in the condenser. And if you remember what the condensers look like, so here I've kind of blown it up, so this is what the condenser looks like. And so this the steam input that's near the saturated vapor is coming in here, and it's dribbling out as a saturated liquid. And we've got all these pipes, which is where the cooling water is running through. This is external to the working fluid in the Rankine cycle, this fluid right in here. And so this is the cooling water, and this is kind of what we're going to be focusing on. So here I show a picture of a actual condenser where the worker here is putting in rods, or these are actually tubes that are going in, and this is where the cooling water is running through. So the cooling water may go in on this side and out the other. So maybe we're looking at this end of the cooling tower there. All right. Now what we're going to be focusing on are cooling towers that are used in order to cool more or less the cooling water. I know that sounds kind of weird. So okay, let's go back to our Rankine cycle. So we've got our working fluid that's moving through here, and then I have the cooling water that's outside of it, and it's running through here. And so what it's going to do is it's going to run through the cooling tower in that direction. So keep in mind that this is going to be relatively warm as it comes off of here, because it's absorbed all the energy during the condenser. And so what I want to do is cool it off so that it can go back somewhat cooler in that direction. And that's going to be the point of the cooling tower. So now let's look over here at the cooling tower. The way that this works, again, so we've got some warm water coming in here. We want it to come out cool, so what we need to do is remove some energy. The way we do it is we're going to go ahead and bring in some water in this direction, or sorry, bring in some air in here. And what we're going to do is we're going to spray this water down. So this is actually not going to be in a closed loop. Spray down. Some of that's going to evaporate and come out in this steam cloud over here. And then what's happening is, since this is coming out as vapor, this liquid down here is going to be cooled. So we're going to be doing energy balances over these cooling towers here. Okay, so let's just kind of put it in context. Let's look at this a little bit more detail. This is actually what a cooling tower looks like. All right, so this is kind of a blow up of it. So here we have the hot water. This is what I call the warm water coming out of the condenser. Yeah, not the Rankine cycle condenser, but this is the cooling water. It's coming in here. It actually gets sprayed out, and then it's going to hit a water distribution system. This is normally just like a grating, more or less, to kind of help break up the water. And then we're bringing air in from down here. So this is normally some kind of dry air. And since this is spraying down, what it's going to do is it's going to become humidified. So what it's doing is it's taking liquid water, moving it into the vapor phase. So it's going to be getting cooled off. And then it's going to go up through the top, and more or less as a kind of the steam cloud that you see. And then as the water continues to dribble down here, since it lost some of its water mass as a vapor, it's going to be cold. And then this can go back to the condenser again. So that's kind of the way that it works. Here you see in this diagram there might be some additional air being input up here, just depending on what's required to get the flow rate through. So that's kind of more or less the way that they look, and that's so much the details that we need to do. What we'll do now is look at the thermodynamics of it. So I've got my cooling tower. So remember, I've got air coming in and then coming out the top there, and then I have water going in that direction. So let's go ahead and number these streams. I'll call it stream 1, 2, and then, oops, there we go. This will be 3, and that will be stream 4. So let's go ahead and look at our mass and energy balances. Now, the air balance here is pretty simple. All the dry air that's coming in here has to be going out there. It's not getting absorbed into this liquid water stream. So it's actually a trivial air balance. But the water mass balance, so this is this top one over here was the air. This is the water mass balance. And so what we have is the mass flow rate of water coming in on stream 3, that's MW3, and then the other one that's coming in is my air, the humid air, so I've got my humidity ratio times that airflow. That's going in, this is what's coming out, and so I have flow rate 4, and then the mass flow rate at W2. And the thing to note is that 3 and 4 are not the same. Since this water is coming and getting sprayed down and some of it's evaporating, the mass flow rate of 3 is going to be greater than the mass flow rate of 4. So you're actually losing water in there, and you actually will need to kind of add some makeup through there, and we'll see that when we solve the problem. So there's the mass balance. If we do the energy balance is pretty simple. We've got our mass flow rates times our enthalpy. So on the left hand side we have in, so mass flow rate of air times the enthalpy of that, and then the mass flow rate of water times its enthalpy. Now a couple things, since this one over here, this first term, this is an air-water mixture, we can get our enthalpy if we have two other variables like maybe the humidity ratios and temperatures. Now this liquid water, this is incompressible, and so normally we can go ahead and approximate the heat capacity as just the Cp times the temperature for that one over here, and the same thing with 4 over there. That will end up being saying that the enthalpy is essentially Cp times T. And so we can go ahead, since it's an incompressible liquid, we can use those approximations for the liquid water stream that's moving through there. Okay. With that, let's go ahead and do an example. And these are pretty straightforward, but we'll go through it. So here's the problem. Let's look at our picture here first. We have air coming in at 20 degrees Celsius and 10% humidity, so it's fairly dry. And then it's leaving at 25 degrees Celsius and 70%. And the cooling water is coming in at 40. We want it to leave at 30. And it's coming in at a rate of 2 kilograms per second. And the two questions we want to answer is, what's the air mass flow rate, so how fast do those fans need to be running? And we also need to know what the makeup water flow rate is, because remember, this one over here is stream 3 and this is stream 4, and those are not the same. Since water is getting sprayed down, some of it's going to get lost. So if we go ahead and look at our mass balance, let's go ahead and write our mass balance for the water. So what we're going to have is we're going to have in equals out, and so what I have is the mass flow rate at 3 coming in, that's water coming in at that direction, and then the other one is I've got the mass flow rate of air times omega 1, that's where it's in the air, and then what's leaving is the mass flow rate of 4 plus the mass flow rate of air times omega 2. So there's my water mass balance. And then the other one I've got now is my energy balance. And again, if I look in equals out, and so what I have going in is I have the mass flow rate at 3 times the enthalpy of 3 plus the mass flow rate of air times the enthalpy at 1 is going in. Mass flow rate at 4 is leaving times its enthalpy at 4, and then the mass flow rate of air times the enthalpy over there at stream 2. And what I'm going to do for H3 and H4 is I'm going to approximate H as Cp times temperature, because I'm given the temperature 40 degrees and 30 degrees. So I will do that for both of those and say H is essentially Cp times T. I just need to know the heat capacity. And I'm in SI units over here, and so the heat capacity of water, liquid water, is about 4.18 kilojoules per kilogram degrees Celsius. All right. So here are my equations, and I'm going to go ahead and just use EES to solve this, so I can look up my properties. I don't have to go to the psychrometric chart. So let's go ahead and move over to EES, and let's look at this problem. So here at the top, what I have are my definitions, and again, remember the air-water functions also take in pressure, so I'm just defining a constant pressure at atmospheric of 101.3. So usually a good assumption. These are operating in the atmosphere. And so what I have is my inlet air, that was 1. So that's the dry air is coming in at 20 and 10% humidity, so RH is 1. Remember, again, relative humidity, if it's 10%, I put down 0.1. And then it's leaving at 25 degrees and 70% humidity, so there's my outlet of the air-water stream. And then the liquid is coming in at 40. I want it to leave at 30, so that's T3 and T4. And I was told what the mass flow rate is going in, so I call that the mass flow rate 3. So that's the mass flow rate of water, 3, and that's going to be equal to 2. All right. A couple properties for liquid water. The heat capacity, as I said, is about 4.18 kilojoules per kilogram. So I can then get the enthalpies of stream 3 and 4 by multiplying Cp times the temperature. And that's what these next two equations are. And now I've got my water mass balance and my energy balance. So this is what we just saw in the previous slide. Mass flow rate of air times W, that's omega, that's the humidity ratio, plus the mass flow rate of 3. And then again, mass flow rate of air times omega 2 times M4, right? And M3 and M4 are not going to be the same. M3 is going to be slightly bigger than M4. And then my energy balance, just the mass flow rates times the enthalpy values. All right. So that's what I've got, and then the last thing I'll do is just have EES look up my properties for me for air, water, and the two things I'm going to need from the mass balance and water balance are going to be humidity ratios and enthalpies. So of the air water mixture, that's streams 1 and 2. So I've got my humidity ratio function, my enthalpy function, and in both those I was given temperature and relative humidity. So I just list those there, and that seems pretty straightforward. So let's go ahead and solve this and see if we got everything we need. And all right, so here's our solution. So if we go ahead and look up it, let's look at our flow rates here. So what I have is the mass flow rate of air. That was one of the first thing it asked for, 2.37. So that's 2.37 kilograms per second of dry air. And then here I have M3 and M4, and notice that M4 is slightly less than M3 because we're losing it, and so we're losing 0.03 kilograms per second of water. So it's the makeup water that we need to add before it runs back into the condenser. So, all right, so those are the solution to that problem. If we come back here, so we just found out what the makeup water flow rate was, 0.03, and then the air flow rate.